Sorry, so now let's talk about hydrate formation. And I'm going to go ahead and do just like I always do, drawing a generalized overview of the reaction. So there's my carbonyl compound of an aldehyde or ketone, and it doesn't matter, it could be either one. And I go ahead and react that. And what I'm going to get with, depending on what my reagents are, I can obviously run this in water, and I can run this in either acids or a hydroxide. Anyways, regardless of whether or not I choose to use an acid or whether or not I choose to use a base in water, what I'm going to get out of this reaction is species as a final formation. This right here is what's called your hydrate. Cool. So that's how that works. My overall reaction there. All that I wanted to mention about this is, obviously this is you can think of it as a H2O addition reaction. We've added a water to it, hence the color coordination over here. Let's just talk about the thermodynamics of this real quick. So if you have an increasing amount of alkyl groups into your compound, you're going to have a decreasing hydrate concentration at equilibrium. And the reasoning for this, whenever we talked about, I guess the generalized structure, I think it was when we talked about carboxylic acids, you got to think of drawing the secondary resonance structure for this. And I'll give an example of what I'm talking about. So let's just compare with us, formaldehyde. Let's compare that with, say, an increasing trend of alkalinity with an aldehyde and with a ketone. We're comparing all three of these, really. So if I go ahead and run this reaction to form a hydrate, so my hydrate formation, just like any reaction, all reactions proceed towards the more stable product. It's going to be 99% hydrate formation at equilibrium. Why? Because hydrates, although they're not this, poster child for a stable species, they're more stable than formaldehyde. This is what happens when you put formaldehyde in a solution anyways. This is why it's a good preservative for a lot of things. Now if I were to react this with an aldehyde, well, okay, I'm going to obviously get about 50%. I'm going to have a 50-50 ratio of this. But the ketone, and it kind of helps if whenever we draw the mechanism, you'll understand this a little bit better. But with the ketone, that's a very stable species. It's not going to have anything that's going to react to it. It's almost going to basically be a negligible amounts. I'm just going to say no reaction. And that's an exaggeration. There's like, my book says that you get 0.2%, which, I mean, that's batshit crazy. No organic chemist on the planet is going to do that. The reasoning for this, though, all kind of comes down to the carbonyl stability. All right, so obviously there's two things that can contribute to the carbonyl stability. That's electron donations and then electron withdrawers. So obviously we have electron donors, and then we have things that are going to be pulling on our electrons. So if you have something that's an electron donor, that's going to stabilize the carbonyl compound, and you're going to have a, relatively speaking, a low hydrate concentration at equilibrium. Why? Because the electron donors, obviously, whenever we draw the resonance structures of each and every one of these, but particularly of a ketone, I think exemplifies this more. We draw a negative charge here and a positive charge here. So if something can donate electrons, it's going to further stabilize that charge there. Now, if we have something that was obviously electron withdrawing, it's going to pull things even more away from our positive formal charge here. So this is going to be a very unstable carbonyl compound. This is going to give us a very high hydrate concentration at equilibrium. Concentration at equilibrium. All right, so let's continue on our discussion that we're having here about hydrates. We can have acid catalyzed hydrate formation, and I'm just going to go ahead and start off drawing out the mechanism. As usual, the first step for anything that's acid catalyzed is a protonation reaction. So you have your generic aldehyde or ketone, and you go ahead and run this reaction in acidic conditions. So I'm going to go ahead and just draw out a generic acid going to leave it kind of in the abstract, but you could also just, well, actually I'll just write it as hydronium ion. And being oxygen with lone pairs, it has that there. We have a proton transfer reaction. Like the others, this exists in equilibrium. If you're kind of understanding, I guess, the reactivity of this, or having difficulty understanding the reactivity of this, draw the minor resonance structure of what you're working with here, and that'll kind of determine the reactivity. I'm going to go ahead and leave it in the major format just to explain the geometry of molecules, but know that reactivity is determined by the second resonance structure. And so now that we've protonated our oxygen, this molecule is far more, you can tell just by looking at it, that's far more unstable than the aldehyde or ketone on the left. And so what this instability leads to is it makes it available now for water, to act as a nucleophile. So I'm going to go ahead and just label that in this little teal color, that the second step is nucleophile attack. And in this context, the nucleophile is H2O. And again, you can draw this in either the major or the minor resonance structure. I wouldn't have a problem with that. But what we end up getting is an oxygen there with an alcohol group attached to that. There's our R prime. And the positive formal charge has passed down to the water here. And again, just like any other one, we have another proton transfer reaction. We run this reaction in water as a solvent. And what you get out of this is your geminal or hydrate that has been formed. This is a pretty comprehensive reaction here. The only thing that you need to notice is, just like with any reaction, it's acid catalyzed, and it's the protonation of the oxygen that makes this reaction proceed in the forward direction. But notice that this is an equilibrium reaction. So just like we added hydrate on, every reaction here is existing in equilibrium. And now from an organic chemist's perspective, I hate seeing that, because that means that I'm going to get mixtures of products that, it depends on what the conditions of my situation are. But I can always look at the nature of my product, and then from that determine what I need to do to get this reaction to move forward. Always keep in mind Le Chatelier's principle when you're talking about this. So I'm going to clear this up and then talk about base catalyzed reactions, which are a bit more straightforward, but they all have the same, I guess, essential steps. And at step one, we have nucleophile attack. There's my aldehyde or ketone, and I'm running this reaction in a very highly basic concentration, which all bases in water give us a generic hydroxide component there. And once we have protonation or nucleophile attack here, we're going to get an equilibrating reaction. And then the second step, I'm just going to do it, categorize it in blue, is protonation. So we run this reaction in, say, sodium hydroxide and water, drawing it like that, kind of in the slang term there. And what we're going to get out of this, as you can see, in equilibrium as well, and I've added a water molecule across that. Cool. Last thing that I wanted to mention was whether or not you're going to be using an acid catalyzed hydrate formation, or whether or not you wanted to use a base catalyzed hydrate formation. And we keep this in the abstract just to save space, but think about whatever the identity of either one of these R groups is, depending on whether you're working with an aldehyde and ketone. And say you have substituents effects that are either acid sensitive or base sensitive, so this is really helpful for the phenomenon of chemoselectivity.